Chapter 6, Probability, Part 4. Probabilities proportions for normally distributed scores. The probabilities given in the unit normal table will be accurate only for normally distributed scores, so the shape of the distribution should be verified before using it. This will be very important when we get into Chapter 7, which is entitled Distribution of Sample Means, or Probability in Samples, the distribution of sample means. So again, the unit normal table is only applicable to normal distributions. In other words, if you have a skewed distribution, whether it's positively skewed or negatively skewed, the unit normal table cannot be utilized. For normally distributed scores, we can transform x values into z-scores, or we can look at the proportions corresponding to z-score value and work backwards and solve for that particular x value. Figure 6.1 refers to example 6.5 of our text, and the question being posed here is, what is the probability of randomly selecting an individual with an IQ less than 120? And we're told that the population IQ average is equal to 100 with a standard deviation equal to 15. So what we're going to need to do, again, the score of interest is equal to 120, and the probability statement is as follows. So what is the probability of randomly selecting an x value, which is an IQ score, that's less than 120? So to proceed, what we're going to do is convert that x value into a z-score using our equation. Z is equal to x minus mu divided by standard deviation. And before we go any further, we should take the time to sketch out a distribution, which has been done for us here, label the mean of the distribution, identify the standard deviation, and then place the score of interest, in this case, a score of 120. And given our probability statement that said less than, we're going to shade this area that's already in blue. And at this point, we can conclude that that area, that proportion that's been shaded, refers to, and I'll ask you, the tail, the area between the mean and the z, or the body. And for those of you who said the body are correct, that is the body. So identifying these things before we go any further is important so that you know what to do next after you solve for z. So z is equal to our score of interest, 120 minus 100, divided by our standard deviation of 15. So our z-score in our calculator is 120 minus 100 gives us 20, divided by 15, and we get a z-score of 1.33. So notice here's our x distribution, and here's our z distribution. So the mean becomes 0, and this x value has now been transformed or relabeled as a z-score, and what that means is an IQ score of 120 is 1.33 standard deviation units above the mean. It's right 1.33 of these, right? To work backwards, we would take 1.33, multiply it by 15, and add it to 100, and we would get a score of 120. So at this point, we have everything we need to find that proportion to answer this question. But at this point, we can convert this into a probability statement using a z-value. So what's the probability of random selecting a z-score that is less than 1.33? And we're going to use our unit normal table to answer this question. So here's the section of the unit normal table that's of interest to us. We enter using column Z, or A, excuse me, which is the z-score. We know the z-score is equal to 1.33, and we're looking for the body of the distribution. So 1.33 is here, and the body is this area here, 0.9082. So our final answer would be reported as 0.9032, or there's a 90.32% chance that if we randomly selected an individual from the population, their IQ score would be less than 120. Figure 6.11 refers to example 6.6 of the text. So the Highway Department conducted a study measuring driving speeds on a local section of interstate highway. They found an average speed equal to 58 miles per hour with a standard deviation equal to 10 miles per hour. And I wrote 5 and it should be 58. Those are givens. The distribution was approximately normal. Given this information, what proportion of the cars are traveling between 55 and 65 miles per hour? Using probability notation, we can express this problem as what's the probability? And again, we have an x value. We're interested, that's going to be, again, we're looking between 55 and 65. So it's going to be less than 65 but greater than 55. So less than 65 yet greater than 55. So that is the area of interest. So the probability of an x value that's less than 65 but greater than 55, and that's that blue shaded area. So again, very important to shade the area of interest. Now this is the process of finding the proportion between two scores, that's one above the mean and one below the mean. And at this point, what we know we need to do is convert those x values into z-scores. So z is equal to x minus mu divided by standard deviation. So for 55 minus 58, and then divide by our standard deviation of 10. So we have 55 minus 58 gives us -3. Divide by 10, and we have a z-score equal to -0.3. Similarly, on this side, same process, x minus mu divided by standard deviation. We have z is equal to the score of 65 minus 58 divided by 10, our standard deviation. So 65 minus 58 gives us 7 over 10, and we get positive 0.7, which we see here. So now we've converted those scores, relabeled them as standard deviation units. So a score of 65 is 0.7 standard deviation units above the mean, and a score of 58, or a speed to be more precise, is 0.3 standard deviation units below the mean. All right, so now we see this blue shaded area, and it's not just one area of interest. We're going to have to approach it by recognizing that this is the proportion between the mean and the z, and so is this. But we're going to look at these two different z-scores and report those two proportions, and as you would imagine, sum them together to identify that shaded area of interest. So again, our z values of interest are -0.3 and positive 0.7. So again, we're going to enter using column A, which is our z value, and here we see 0.3. The area between the mean and the z is the area of interest, so that's 0.1179. And we go down column A and see that we don't see 0.7, so we'll need to go to the next page. So 0.7 is on this page, and we see it here. And the area between the mean and the z is 0.2580. So we're going to use both of those values and then take the summation to find the proportion of speeds, or a proportion of the distribution of speeds that falls between 55 and 65 miles per hour. And I should restate that. It's actually the proportion of cars that are driving between 55 and 65 miles per hour. So we found that this proportion here was equal to, for a z-score of 0.7, this was 0.2580, and this was the z-score of -0.3, corresponded to an area between the mean and z of 0.1179. And I'm going to clear up some of this so that we can see this a little easier. So we can take that original probability statement and now use it in reference to the z-scores. So the probability of a z-value that is less than 0.7 but greater than negative 0.3. And again, it's the process of taking this area here and adding it to that area. So we take 0.1179 added to 0.2580. So in our calculators, let's take the summation of those two proportions, and we should get a proportion equal to, so to answer this question, we would respond that the proportion of cars traveling between 55 and 65 miles per hour is equal to 0.3759, or we could think of it as there's a 37.59% chance that if we pulled someone over, they would be traveling between 55 and 65 miles per hour. So again, this example illustrates the area between a negative z and a positive z. We're going to be referencing the concept of percentile ranks quite a bit. So we need to understand what that refers to. How do we define percentile rank? So percentile rank is a percentage of individuals in the distribution who have scores that are less than or equal to that specific score. So let's say on exam 1, you were told that you scored at the 90th percentile. Any standardized assessment such as the SAT or K through 12 standardized assessments are reported as percentiles to give you a sense of how you did in relation to everybody else. So if someone said you scored in the 90th percentile rank, we know that that means 10% was here and 90% here, but we always read it at this value and anything that occurred below. So it means that 90% of the population scored less than your X value, and only 10% scored above you. So again, the 90th percentile means that 90% scored below you, but it also refers to 10% scoring above. But we always read it in terms of this direction, what happened below that particular score. So the percentile will identify the percentage below a specific X value. Probability questions can be rephrased as percentile rank questions. So again, we can use these words interchangeably so that we focus on one element versus another, but recognizing the equivalency of some of these terms. Before we move into an example of percentile rank, let's do one more example of finding the proportion between two scores. And we'll use the driving speed example as a foundation. So again, the average speed was 58 miles per hour with a standard deviation equal to 10 miles per hour. And now we're interested in looking at the probability using the same driving speeds, what proportion of cars are traveling between 65 and 75? So again, we're looking at below 75 yet above 65. So we have X value that is below 75 miles per hour yet greater than 65 miles per hour. And we know that we're going to need to convert both of those values into z-scores. So the first one, z is equal to x minus mu divided by standard deviation. 65 minus 58 divided by 10. And we get 65 minus 58 is equal to 7. Divide by 10, and we get 0.17. So that's the new label for a score of 65. And for 75, again, z is equal to x minus mu divided by standard deviation. Z is equal to 75 minus 65 divided by 10. Z is equal to, we have 75 minus, oops, I made a mistake there. I'm going a little too fast. So I was subtracting the other score when it should be the mean of 58. So 75 minus 58 divided by 10. 75 minus 58 is 17 divided by 10. So z is equal to, 1.7, which is this z-score here. So again, we relabeled that score. And now this area of interest has been shaded in the blue, and we should be perplexed a bit because now you should realize that there isn't one specific area. This shaded area is not the tail, it's not the area between the mean and the z, and it's not the body. So how will we go about finding this area of interest? Well, if we use our understanding of the characteristics of a normal distribution, one way that we can approach this is to recognize that from here to here would be the tail for the score of 65. And this unshaded area, right, this unshaded area would also be the tail, but in relation to this value. So we could find the proportion, the tail, right, that's greater than 65, and then recognize it includes this area of interest, the blue area, and it also includes this unshaded area that we're not interested in. So what we could do is find this proportion from here to here, the area above a score of 65 or a speed of 65, and then subtract out the tail for the proportion above speeds of 75, and what will be left over is this area of interest. So let's do that. So we have our z-scores, and what we're going to do is report the tail for both. So the z-scores of interest are 0.7 and z equal to 1.7. So I'm going to find those here, and again, the tail is the area of interest. So 0.7 and 1.7 will be on the next page. So the tail here is 0.2420, and 0.7 is here, and that proportion is 0.0446. So I'm going to use both of those values and use the graph to then figure out that area of interest. So we found that from here to here, the tail for the score of 65, or z-score of 0.7, that was equal to, that's the larger proportion of the two, was equal to 0.2420. And then this tail here, right, corresponds to x value of 75 and a z-score of 1.7, was equal to 0.0446. So again, this larger area, we're going to subtract that proportion, and what will be left over is this area of interest. So again, our probability statement can be restated using a z-score. So a z-score that's less than 1.7, yet greater than 0.7. And again, we're going to use these two proportions. So in your calculator, take 0.2420 and subtract 0.0446. And what you should come up with is a proportion of 0.1974, or 19.74%. So the initial question was, what is the proportion of cars that are traveling between 65 and 75 miles per hour? And the proportion of the distribution would be equivalent to 0.1974, or there are 19.74% of cars traveling between these speeds. So that percentage shows that approximately 20% of people are driving beyond the specified highway speed, acceptable highway speed, and could warrant receiving a speeding ticket as a result. So again, here we dissect the distribution according to what we know and what we can use in the unit normal table to solve this type of problem. In the previous examples, we were asked to find the proportion or probability that related to a specific x value. The two-step process for finding these proportions is shown in this figure, figure 6.13. Thus far, we have only considered examples that move in a clockwise fashion. So we begin with an x value, we transform it into a z-score using our z equation, and then we use our unit normal table to find proportions or probabilities. That's what we've been doing thus far. But we should also realize that it is possible to reverse this process and begin with an x value. So we'll begin with the x value, in the reverse fashion, we'll be able to solve for an x value. So in that case, we have a specific proportion identified, and then we look up the corresponding, so we begin here using the proportion, then we use the unit normal table to identify z-score, and then we solve for x. So again, that process, we're solving for x, mu plus the product of the standard deviation multiplied by the z-score. And this will relate to the examples that pertain to a percentile rank. So a couple slides ago, I defined what a percentile rank refers to. It's the percentage of scores below a certain x value. So always reading to the left, that percentage to the left of that specific x value. So figure 6.14 relates to example 6.8. The U.S. Census Bureau in 2005 reports that Americans spent on average 24.3 minutes per day commuting, and with a standard deviation equal to 10 minutes. How much time do you have to spend commuting each day to be in the highest 10% nationwide? Probably not the group that you want to belong to. So we're going to figure out how much time you spend commuting each day that would place you in the top 10%. So again, we're going to focus on this, and we are going to partition off 10%. This is the top 10%. And what we need to do is convert that 10% into a proportion, so we can utilize our unit normal table. So we're working with a proportion of 0.1000, and we know that this represents the tail, so that's how we're going to enter the unit normal table. And what we want to solve for is x. What is the amount of time spent by a commuter that places them in the top 10% nationwide? So it's mu plus the product of our standard deviation multiplied by our z. Let's replace the variables that we know. We know that mu is equal to 24.3. The standard deviation was given, which is equal to 10. And what we need to find is z. What is z equal to? So we're going to use this 0.1 proportion and report z that corresponds to that area. So again, we don't enter using the z because that's what we're looking for. We're trying to identify what z is. But we have the proportion in the tail, and that was equal to 0.100. So we're going to use the tail column and find the closest proportion to 0.1. And so we're going to go down, and we're getting closer, and we find that 0.1003 is the closest, and it corresponds to a z-score of 1.28. So z is equal to 1.28. And now that we have that, we can solve for the question at hand. Again, we wanted to find out what is x equal to here. So we solve for x, 10 times 1.28, and then added to 24.3. So 24.3 plus 12.8, the product of the standard deviation multiplied by z-score, and that gives us 37.1. And so now we've solved this particular problem, which was to identify the minutes commuting that places somebody in the top 10%. Now, something interesting to point out with this particular example, if you spend 37.1 minutes commuting to work, Does that place you in the 10th percentile or the 90th percentile? I'll give you a second to think about that. Are you in the 10th percentile or the 90th percentile? If you answered the 90th percentile, you would be correct, because by definition the percentile rank is always read at that score and anything below. So we would see that 90% of commuters spend less time commuting to work than you do, and 10% spend more time than you do. But again, this problem, we were talking about the highest 10%, so this is the way that we approached it. But this question could have also been stated as a percentile question, and it would have stated, identify the commuting time that represents the 90th percentile. And we would use the same process. The only difference is that we're focusing on the 90th percentile score versus the top 10, but they're the same value. The x value would be the same. So this example 6.9 for figure 6.15, commuting time distribution, we're using the same information from the previous example. So the average commute time is 24.3 minutes with standard deviation equal to 10 minutes. And now we want to find out what is the commute time that frames the middle 90%, the middle 90% of this particular distribution. So again, this area that's shaded is not one that is in the unit normal table, but if we think of it as half, again, this area here could be seen as the area between the mean and the z, as is this area. So what we need to do first to convert our x values into z-scores. So z is equal to, and I retract that, and we're not solving for z because what we want to find out is what z is. We want to solve for x, and that's what we want to solve for, x on both ends of the distribution. And what threw me off is the answers are already provided here on this slide. That what we want to do is solve for x, mu plus the standard deviation multiplied by our z-score, just like we did in the last example, but now we're working with two values, one on either side of the mean. So to solve for x, we're going to solve for x twice. So let's replace our variables. So we know that the mean is equal to 24.3. Our standard deviation is 10, and then we're going to find what z is equal to, and we're going to have a positive version of z and a negative version of z. And they would be the same if they're equal distance from the center of the distribution. So again, this area in the center is defined as the middle 90%. If we split that in half, we would recognize that this is representative 0.4500 and 0.4500 here. All I did was take 90%, right, divide by 2, or a proportion of 0.9, and we get 0.4500. And now, using that information, I can utilize my unit normal table and find the corresponding z-score. So we're looking for the proportion in the area between the mean and the z, which is column D. Column D, and we're trying to find out what z is equal to. And the proportion that we identified of interest is 0.45. So we're going to look for that in this column here. And this is a good example to discuss. Here we won't find 0.45 exactly, but we find these two values that are equal distance from this area or proportion that we're looking for. So we have a value of 0.4495 and then a proportion of 0.4505. Now, normally the rule of thumb is use the proportion that's closest to the proportion of interest, but in these two cases they're exactly the same distance from that one. So technically, reporting a z-score of 1.64 and 1.65 would be considered accurate. And you know, I would never give you a test question where you would have to make that determination, because either would be fine. But for purposes of saying that we want at least, at minimum, 90% in the middle, we're going to go with 1.65 because that proportion is going to be 0.4505 times 2, and at minimum we're going to get 90% in the center. The other proportion multiplied by 2 is going to be something less than 90.9 or 90%. So the reason we select 1.65, again, either would be fine, but unacceptable. But we use the 0.4505 so that the middle area of interest is going to be at least 90% because that was the focus. So we're going to report Z is equal to positive and negative 1.65. And the reason for the positive negative is because we're working with a proportion less than, or a z-score less than the mean and a value above. And I'll show you that on the diagram. So again, this has already been entered for us because that proportion is equal. So this location, right, this area, it corresponds to the mirror image on the other side. So we're talking about a score that's 1.65 above the mean and 1.65 standard deviation units below the mean. And so now we can solve our equation. We have our mean of 24.3 minutes plus a standard deviation of 10 minutes multiplied by positive negative z-score of 1.65, and in doing so we get x is equal to, so again we have two different answers, 24.3 plus 16.5 is equal to 40.8, and then we would solve for x is equal to 24.3 plus negative, right, our negative value of 16.5. So x is equal to 7.8. So instead of adding 16.5 to 24.3, we're subtracting it from that value to give us this x value here, and we solve for this x value. So again, isolating the area of interest using our understanding of the different columns of the unit normal table to identify an area that we can enter the unit normal table and find the corresponding z-score. So we'll end this chapter with a learning check, or end this lecture portion. And the question is, membership in Mensa requires a score of 130 on the Stanford-Binet 5 IQ test, which has a mean equal to 100 and standard deviation equal to 15. What proportion of the population qualifies for Mensa? So we have our distribution. The mean is set at the center, 100. One standard deviation unit is equal to 15. And the score of interest is 130, which would be to the right. And we would say it requires that they have that as a minimum. And so we would know that anyone who has 130 or greater, right, would qualify. And so this is the tail of the distribution. So to answer this question, we're going to need to convert this into, this is our x distribution, into z-score. This becomes 0. Z is equal to x minus mu divided by standard deviation. Z is equal to 130 divided by 1. That's not right. It's talking much faster than I need to. 130 minus 100 divided by our standard deviation equal to 15. So we have 30 divided by 15, and we get a z-score equal to 2, which should convey an image of something very rare and unusual and having low probability. The sketch here tells us that we could automatically eliminate at least one. We know that B is not going to be an option because that's almost the entire proportion of a normal distribution. And it would be safe to say that C is not an option because we're so far away from the mean that 2 standard deviation units places us in an area that this would not be a viable answer. So we're going to choose between these two, and to finalize our answer, we simply look up a z-score of 2 and report the tail. So here is a z-score of 2, and the tail is equivalent to 0.0228. And now we've answered our question. So we, again, could have stated this as probability, the probability of an x value greater than 130, which is equivalent to a probability of a z-score greater than 2, and we came up with an answer equal to 0.228. So only 2.28% of the population would qualify for this group of highly intellectual individuals, people with very high IQs. Okay, so true or false? It is possible to find the X score corresponding to a percentile rank in the normal distribution. So yes, we talked about that. You know, the 90th percentile score can be found, and again, we're solving for X, so mu plus our standard deviation multiplied by our z-score. So we're going to need to, again, these will be givens, given values, and to find the z-score, we'll just need to convert that percentile rank into a proportion. So percentile rank converted to proportion, which would then enable us to enter the unit normal table to find the missing z-score, and then we can solve for x. So that is true. If you know a z-score, you can find the probability of obtaining that z-score in a distribution of any shape. What was the requirement of using the unit normal table? The requirement is that it is normally distributed, so normal distribution. So again, normal looks like this. So we couldn't apply it, these procedures, to skewed distributions. That would be improper. So this is false. The shape required is a normal distribution. And that concludes this part of the lecture. In the next video, we'll be looking forward to inferential statistics, of how this all relates to the process of drawing conclusions about populations using samples, and will lead us into the next chapter, which is probability of sample values when we're working with a distribution of sample means.